So good afternoon, everyone. So thanks, Laurie, for the introduction. So I'm Qian. I'm an assistant physicist here working in this great lab. So first, I would like to thank Laurie and the committee member for asking me to give this year's Asymmetry lecture. And second, to my knowledge, I think many of you are actually undergraduate students. I think some of you are high school students. And I want to say that I'm very impressed that all of you are so young and so brilliant, but take the interest to come to our lab to learn about the research and learn about the science. I still remember when I was about your age, I was more into computer games. I like to play StarCraft, Counter-Strike. However, I have been always intrigued by the beauty of the science and also the research work in which scientists can unlock the mystery of the universe step by step using various methods. So that's why I would like to take this opportunity to talk about how we're doing research. And in particular, I want to, as an example, I will display you the ongoing journey that we physicists are taking to seek the origin of the asymmetry. So here's the outline of the talk. So the big question that we're trying to address here is why is there a much more matter than antimatter in our universe? So everything you see, you touch is made of matter, and why is that? And then the related question is whether a neutrino is the key to these big questions. And then after that, I'm going to talk about some details about how to answer this question or how to investigate whether neutrino is the key of this question. So basically, when you start to do research, you always start with very big questions, and then the research is like you convert this big question into a set of smaller questions and hopefully simpler, and then you try to answer those smaller questions one by one. And hopefully, by the end of the day, you address all the smaller questions, and you also answer the big one. So in this case, I was going to talk about the two experiments, the diabatic experiment, reactor experiment, and the microboom experiment, which actually address two of the important questions, smaller questions. And then I will talk about, touch a little bit at the end of it, the mega science project. People here have been working very hard. This deep underground neutrino experiment, which is designed to address this question and also some of the future challenges. For this, I'm sure that many of the future challenges that are required to be solved by the younger generation of scientists, like you. So this plot summarizes our current understanding of the history of the universe since the Big Bang about 13.8 billion years ago. So at the beginning of the Big Bang, you generate quark and the leptons, which is matter. And then you have anti-quark, anti-leptons, which is antimatter. And then they start to evolve. And one important time scale, this 10 to minus 10 second, like 0.1 nanosecond after the Big Bang, is basically the time scale here. The RIC, the heavy ion collision, is probing. And then the quarks would form nucleons and mesons. And then later, the nucleon would form nuclei. And then you have atom. And then the molecule, and for example, the large structure as we see today. So it is expected that at the beginning of the Big Bang, the equal amount of matter and antimatter were produced. However, nowadays, you can see all we see is matter. So there is this huge asymmetry between the matter and the antimatter. And we need to, the big question here is where is all the antimatter? So scientists use a variable eta, which is a ratio of the number of baryons. It's like the number of matter divided by the number of photons, which is resulting from the the matter-antimatter annihilation. Define this number. Use this number to quantitatively describe the symmetry. So using the different method, this number was measured to be about 6 times 10 to minus 10. And it looks like a very small number, but it's actually very big because if you have an equal amount of matter and antimatter, this number should be 0. So to understand this matter-antimatter symmetry, there's a very important concept that we need to talk about, which is a CP violation. So the parity operation is basically you have a coordinate space, you have an x and a y and a z, and after you have a parity operation, you basically go to the next negative x, negative y, and z. And similar for the time reversal, basically the time, change it to negative time. And then you also have the charge symmetry operation, so where if you have an electron, you apply this symmetry operation, it becomes a positron. So the important message here is that so when you have a CP violation, the charge parity symmetry violation, what it really means, it means that the physics law governing the interaction of matter are different from those governing the antimatter. So you can imagine you start with the equal amount of matter and the antimatter, but in the evolution, the evolution is governed by the physics law and they are different, then it's possible that at the end of the day, you have more matter left. So then the natural question you want to ask is there any CP violation exist in the standard model of particle physics? So, so this standard model of particle physics is a model that we established about like 40 years ago, which describe almost all the experimental observations we have in the high energy and nuclear physics. So it consists of 6 quarks, and up, down, charm, strange, top, and bottom, and then 6 leptons, and the 3 of them are charged leptons. You have electron, muon, and tau, and then the 3 neutrinos. We'll talk more later. And they also have these 4 bosons corresponding to the forces. So you have the gluons, which is the mediator for the strong interaction. And then you have the photon, which is responsible for the electromagnetic interaction. And then the W and Z bosons for the weak interaction. So these are the 3 out of the 4 fundamental forces we have in nature. And of course, we have this famous Higgs boson, which is responsible to give mass to some of these particles. So let's back to the original question. Is there a CP violation existing in the standard model of particle physics? So the answer to that question is yes. The CP violation exists in the quark sector. But if you take what we know and start to calculate what this eta should be, and you will find an answer which is like several orders of magnitude smaller than what we observed. So basically, although the CP violation exists in the quark sector, they are not enough to explain what we observed, so why we are all made of matter. So then you look at this plot. Another natural place to start to look for the CP violation is the lepton sector. So the natural question is there a CP violation in the lepton sector which is responsible for this large asymmetry? So from now on, I'm going to shift to the details about the neutrinos, and then basically trying to search for a new CP violation in the neutrino sector. So at the beginning, I want to first give you some facts about the neutrinos. So neutrinos are this fundamental particle in the standard model. So it's a spin 1/2 fermions. It carries 0 electric charge, so it interacts through the weak interaction. So if you have a neutrino and you try to stop it, and it will take a wall thicker than our galaxy to stop it. So it's very weakly interacting. It's very difficult to do experiment with neutrinos. And in the past 20 years, we also learned that the neutrino have a non-zero mass. So this is actually the physics, the clear physics beyond the standard model. And then because of that, actually, if you calculate the mass budget or energy budget, in the universe, and you would find that, basically neutrinos are responsible for larger than 0.3% of the energy budget for the universe. In every cubic centimeter, you have 300 neutrino and antineutrinos coming from the Big Bang. And this number looks like small, but just for give you an example, the electron, which you have in all the matters, so the electron's contribution is smaller by at least an order magnitude than this 0.3%. So the neutrino basically is a very important part of our universe. And also, the neutrino's mass is non-zero but very small. It actually also suggests a new mechanism for the mass generation. So in addition, we have the Higgs mechanism, as we talked before, And then we have the, for the nucleon, the mass of the nucleon is mostly coming from this, energy, Einstein's famous equation, E = mc squared. And this smallness of the neutrino mass, also suggests a new mechanism, the third mechanism for the mass generation. So, neutrinos, we found that not only the neutrino has mass, its mass eigenstate also is not equal to the flavor eigenstate. So what it means that you have basically in the standard model, you have these three flavors of neutrinos, the electron neutrino, muon neutrino, and tau neutrino. So the way it is defined is basically electron neutrino would can convert into an electron, and the muon neutrino would convert into a muon, and tau neutrino convert into tau. So you cannot have a muon neutrino convert to an electron directly. So that's the way we define the flavor or the flavor eigenstate of the neutrinos. And then this flavor eigenstate is not equal to the mass eigenstate. So what it means is if you pick a mass eigenstate, let's say a nu 3, so it is a superposition of the three flavor eigenstates. So naively, basically part of it is the electron neutrino, part of it is the muon neutrino, and the part of it is the tau neutrino. And because of this, this inequality, actually you have a very famous quantum mechanics phenomenon, which is a neutrino flavor oscillation. So I'm going to illustrate this using a simple two-neutrino model. So in this case, you have a neutrino flavor eigenstate labeled by alpha and nu beta, and you have the mass eigenstate. They are not equal to each other. So their relation can be described by a 2x2 matrix, and then can be further parameterized using this angle theta. So this neutrino oscillation happened because the neutrinos are produced and detected by the weak interaction. However, when they propagate in the vacuum, they propagate as mass eigenstates. So you start with a nu alpha state, and basically part of it is nu 1, part of it is nu 2, and then they propagate in the vacuum. Each of them will pick up some phase, which is different from the other, out of the propagation. And it's the interference of this phase lead to a one neutrino flavor change to another neutrino flavor. So we have the so-called appearance channel is where you have a neutrino change its flavor. And the probability of that is proportional to the sine squared 2 theta. Here, theta is the mixing angle. And then this additional term, which depends on the mass square splitting of the mass eigenstates, the distance of the neutrino travel, and the neutrino energy. And then we usually have the so-called survival or disappearance probability, which is just the 1 minus the appearance probability. So in reality, things are much more complicated. We know in the standard model, we have 3 flavors of neutrino rather than 2 flavors of neutrino. So in this case, the matrix is actually a 3x3 matrix. And you can parameterize it using a 3 mixing angle and the 1 phase, the phase which is responsible, potentially responsible for the CP violation. So instead of giving you a very, very long formula to illustrate how this neutrino oscillation happens with the 3 flavors, we use this plot. So this is illustrated as a 1 GeV muon neutrino and versus the probability of the basic different composition versus the distance it travels. So you can see at the beginning you start with 100% of muon neutrino represented by the white. And then some of them, a lot of them would move to this blue, which is a tau neutrino. And then a little bit of them can move to this electron neutrino. And then if you zoom in to this place, you can see there are 2 dashed green line, which represent, is a comparison to the boundary which separate the blue and the red region. So what these 2 lines means that it's basically a different value of the CP phase. So naively, what it means that if the neutrino to the muon neutrino to electron neutrino oscillation probability, if we take the bottom line, this is a bottom dashed green line, then for the anti-neutrino, naively it will take the upper line. So you basically will have a difference between the probability of a muon neutrino oscillate to electron neutrino versus the anti-muon neutrino oscillate to anti-electron neutrino. So that means you have a different physics law governing the matter and the antimatter. that would be a clear indication of the CP violation in the neutrino sector. And that is what we are looking for. So now you have a reaction where you can use to search for the new CP violation, and then you want to design an experiment. And in order to do that, the first thing you need to find for neutrino is to find a neutrino source. So this is a plot made by Millen, which illustrates that what are the available neutrino sources we can access on the Earth. So first, we have the electron neutrino coming from our sun. So that's coming from the fusion process. And then we have anti-electron neutrino generated from the reactor power plant. So this is due in the fission process. And then when the high-energy cosmic ray hit our atmosphere, it will generate mesons, pions, and kaons. And when they decay, they would generate some neutrinos that you can use. And then you can also produce neutrino in the lab. So you can use a very, say, energetic and intense proton accelerator and use them to hit the target to generate meson, pions, and kaons. And then you can use the magnetic field to focus them, and then let them decay. And when they decay, they will generate neutrinos. And then you can use those neutrinos to do experiment. So since our focus is in this appearance channel, this nu mu to nu e appearance, and then you want to do the appearance channel, and then you can look at all the different available sources. So first, you can look at the electron neutrino and the anti-electron neutrino. So the energy of them are too low. So you don't have enough energy to produce, say, a muon, which is energy is much higher than the MeV range, and then you cannot produce tau. So if you look at all the four sources, actually, so the proton accelerator accelerator beam neutrino experiment is the one that you are looking for, where you can produce a clean muon neutrino beam, and then you can also produce anti-muon neutrino beam and try to measure these two probability. So here is a periodic summary. So in order to find the origin of the matter-antimatter asymmetry, we basically decided to look at the neutrino sector. It's a natural place to look. And with all the available channels and the practical constraints that we have, we decided to search this new CP violation using the muon to electron appearance oscillation channel, and basically trying to search if there's a difference between the muon oscillate to electron neutrino probability versus anti-muon neutrino and anti-electron neutrino oscillation probability. And then, then once you have that strategy, there are more questions coming. For example, is this possible? And how you're going to detect it? So first, so this plot we showed it before represents basically the probability for a muon neutrino oscillate to electron neutrino. It represents by this red band. And if you remember earlier, we mentioned that this probability is proportional to the sine square 2 theta. And here, theta 1,3 is one of the three neutrino mixing angles. So the value of this theta 1,3 was unknown prior to the 2012. So what happened if the angle of theta 1,3 is 0, then you would have no difference. So everything basically becomes 0. There will be no difference between the solid line and any of the dashed line. So in this case, it makes it impossible to search for the CP violation. So in order to know the value of theta 1,3, so basically we need to design a new experiment dedicated to measure the theta 1,3, and that is the Diabet reactor neutrino experiment. And this also illustrates the beauty of the science. So the science basically is where you can do something, you can measure something, and then with the knowledge you gain, you start to have a predicting power. So this one is the same theta 1,3 is also responsible for the anti-electron neutrino disappearance channel. So if the theta 1,3 is not 0, you're going to have a dip at about like a 2 kilometer for the anti-electron neutrino. So some of them will oscillate to other flavors. So if you observe such a deficit, then you would know that this nu mu to nu e oscillation is possible. It's not 0. So the Diabet experiment used one of the four neutrino sources we have, the reactor anti-neutrino source. So it's produced in the fission process. So in every fission, there will be about 6 anti-electron neutrino produced. So it means that it's about 2 times 10 to the 20 anti-electron neutrino produced every second per gigawatts power. But the neutrino is extremely weakly interacting. So if you have 1 ton of target put at 1 kilometer, and then you wait 1 day, you would see 1 event for every gigawatts thermal power. So it's really, the rate is really low. And then the way we do it is the inverse beta decay to detect the neutrino is the inverse beta decay. So where you have anti-electron neutrinos come in, interact with the proton inside, the target free proton inside the target, and convert into a positron, and then leaving a neutron behind. And this positron charged particle will ionize in the detector, and then generate the optical photons, which you can detect, you can see. And then the neutron later will capture by a nuclei and generate more photons, later change to optical photons, and you can also see. So it is a coincidence signal where you can detect anti-electron neutrino. So the diabatic experiments, the experiment located in the southern China is near Hong Kong in this diabatic reactor complex. And its main purpose is to produce electricity for Hong Kong. And it's a powerful reactor complex, and there are 3 reactor core pairs, and they each contain 2. And then the total power is about 17.6 gigawatts thermal power. And then in this experiment, we have 3 experimental sites. You have 2 so-called near sites. Each contain 2 detectors whose goal is to monitor the activity coming from the reactor cores. And then you have a far side, which is about 2 kilometers, where the deficit you expect the deficit is. You have 4 detectors, trying to measure the potential deficit. So the diabatic experiment is the largest and the deepest reactor CETA-13 experiment in town. So in order to reach high precision, so you really need to have enough events, so very high statistics. So we combine very powerful reactors with a very large target mass. It's 80 tons of target mass. And then you also need to control your systematic uncertainty, basically go to high accuracy. And then we use the so-called ratio method where to cancel a lot of the potential systematic uncertainties. So this is a kind of like what do we measure? We measure the events, ratio, events in the far detector divided by the number of events we observe in the near detector. So naively, if there's no oscillation effect, you would expect this number of events follow a 1 over r square law. So the further distance you go, the less events you would see. And the neutrino oscillation effect would basically present itself as this additional deficit on top of the 1 over r square law. And then we also try to control the detector related systematic uncertainties, and also try to reduce the background. So the centerpiece of our experiment is this anti-neutrino detector. It's about 5 meters in diameter and 5 meters in height. And it has the 3 zone design. So the most inner zone is contain 20 tons of gadolinium-loaded liquid scintillator. So that's the main target region we have. And then it's separated by an acrylic vessel. The second layer contains about 20 tons of pure liquid scintillator. And then the third layer is 40 tons of mineral oil, try to suppress the background coming from the outside. And then we have about 192 photomultiplier tubes, which is sensitive to the optical photon, which is to observe the neutrino interaction. And they are installed on the wall. And then we further have a reflector, an optical reflector on the top and the bottom to effectively increase the photon coverage. And then on the top of the detector, there are 3 of automated calibration unit, which we can periodically calibrate our detector. So this is a picture of this one of our anti-neutrino detector. So moving from the the assembly building to the site. And we place this anti-electron neutrino detector inside a water pool. The water pool is actually constructed by the physicists here at the physics department. And it's immersed in a water pool, and is used to shield the radioactive background coming from the environment, and also serve as a detector to tag the cosmic muons. So this is the first detector configuration that we have. We have a 2 detector installed in the first experimental hall, and 1 detector installed in the second one, and then the 3 detector installed on the third one, on the far hall. And then we started data taking around Christmas 2011. So in the year of 2011-2012, there was this intense competition among the many different experiments and using different techniques and trying to get the value of theta-1,3. So prior to Diabet, you can see there's a few hints, give us some hints that theta-1,3 might be not zero, but the uncertainty of the measurement is large, so it's not conclusive. So in March 2012, the Diabet collaboration, we reported the discovery of the non-zero value of theta-1,3 with a significance larger than 5 sigma. So what you have on this plot shows the detected number of events divided by the expected number of events, which can be calculated using this 1/r² law. And then you can see if the neutrinos follow this 1/r² law, it will have basically a line at 1. And our data clearly show this additional deficit means some of the anti-electron neutrino disappeared as they travel to our detector. And this is clear evidence for non-zero theta-1,3. And our result was selected as one of the top 10 scientific breakthrough in the year of 2012 because we finally know theta-1,3 is not zero, and we can search for this new CP violation in the neutrino sector. So is this approach viable? Yes, we did an experiment, and this experiment, we are very lucky that the nature tells us theta-1,3 is not zero, it's about 8.4 degrees. And then the next question is how you're going to detect the signal if you do such an experiment. So let's first remind you what the signal looks like. So what the signal we're looking for is a muon neutrino oscillate to electron neutrino, this appearance channel. So what I'm showing here is the probability of this muon neutrino oscillate to electron neutrino at a fixed distance, 1,300 kilometer, versus the neutrino energy. And the different curves represent the different value of the CP phase. So if this phase is not 0 nor pi, you basically have the CP violation in the neutrino sector. And as you can see, this probability, the pattern of the probability are very sensitive to the value of the CP phase. So if you can precisely measure this pattern and also do it for the antineutrino, then you can search for a CP violation. And as we mentioned, the signal here is the electron neutrino can only convert into an electron. So you're basically looking at a signal, the final state, which contain an electron. So in an accelerator neutrino experiment, similar. First you need to find the beam, so which is accelerator neutrino beam. It's energetic proton. A proton beam collide with target and generate pions and kaons, and you use the magnetic field to focus them, and then let them decay, and they will generate for them the muon neutrino. And similar to the Diabet experiment, in order to measure the oscillation, you need to have a detector at a certain distance, which is sensitive to the neutrino oscillation. And at the same time, you also want another detector very close to the beam to help you to categorize the neutrino beam. So this is a typical configuration of an accelerator neutrino experiment. So throughout the world, there's basically 4 neutrino beams in the recent years. So there are 2 of them in the United States, in the Chicago Fermi Lab. There's a booster neutrino beam using the 8 GeV proton. And then there's a neutrino beam from the main injector using the 120 GeV proton to hit the target. And then there was one in Europe, the CNGS beam. And then there's one in Japan, the JPark beam. And so what we want to do is to get this signal out. And in the next two slides, I'm trying to convince you that the channel we are looking at is extremely complicated. So we need a very powerful detector to help us to figure them out. So first, if you look at the beam, actually what you really want is a muon neutrino beam. But actually, there will be some contamination coming from the anti-muon neutrino and also the electron neutrino and the anti-electron neutrino. Because you have the meson decays. So, for example, if you have your main signal is coming from the positive pion decay, so if you have a negative pion decay, you would have some of the contamination come from the anti-muon neutrino. So despite our effort to make a pure muon neutrino beam, it always contains 4 species of the neutrinos. And then each of them can have a charge current interaction. Again, the electron neutrino will convert into electron, muon neutrino can convert into muon, and you also could have the tau neutrino, which is oscillated from the muon neutrino to generate some tau. And then, of course, you can also have a neutral current interaction where the neutrinos come in and the neutrino leave, and then leave, for example, a break nuclei. So what we want is to have a detector which can really pick up this channel out of all the other channels we have. And this is not complicated enough, because if you just look at one of the channels, so let's just focus this particular channel. We have a neutrino, muon neutrino interact with nuclei. This one is actually have many different reactions, because what you are interacting is a nucleon inside the nuclei. So you're using the neutrino to you can understand as a probe the nucleon. So in this case, you can imagine when the energy is low, what you are probing is the entire nucleon as the entire object. So you would have this nucleon coming in and the nucleon going out. But then if you put more energy into the system, into the nucleon system, then you could excite the nucleon and go to an excitation state, and then it will decay. The final state will contain, it's more complicated. But then you could have even more complicated, because if you have enough energy, you can start to probe the underlying structure, the quarks, antiquarks, the photonic structure, inside the nucleon. And this is go to the deep inelastic scattering, and you can see many, for example, meson coming out. And you can see, depending on the energy, you have a different portion of each process. So this plot shows the neutrino cross-section, basically the probability of each reaction happens. So you can see it's actually, you can have all 3 of them. Depending on the topology, you can imagine you could have a different strategy to, for example, reconstruct the neutrino energy. And you can have also a different strategy, try to reduce the background for different channels. So what we want is to really have a detector which can differentiate all these channels and also all the different reaction process we have in this slides. So the requirement of the detector technology is the capability of an excellent differential power between the signal and the background, and for various channels. And also the detector need to be large. We need to build like tens of kiloton detector, because the neutrino interaction rate is so low. So the answer to this question is this technology we have been developing at Brookhaven, this liquid argon time projection chamber, which can take a 3D image of the neutrino interaction. So let me first tell you the working principle of a liquid argon time projection chamber. So you basically have a bulk of liquid argon, and when the neutrino interact with argon, it will generate a few charged particles. And then when the charged particle moves through the liquid argon, it will ionize some of the electrons from the argon atom. And then you can apply an electric field, and then the ionized electrons would move along the electric field, and then it will reach, for example, an anode plane. So in this case, if you have a detector plane installed in the anode plane, then from the location where the ionized electron hit, you would know its position in this plane. And then the ionized electron also move at a constant speed inside the liquid argon. So at 500 volts per centimeter, the electric field, it moves about 1 mile per second. So in this case, if you know when the event happened and when the signal reached the anode plane using this time difference, then you can calculate what's the distance this event happened. So you can really take a 3-dimensional image of the neutrino interaction with a position resolution about millimeter. And also by counting how many of ionized electron you collect is sensitive to the energy deposition you have for the charged particle inside the liquid argon, and then you can identify this particle. And also, very luckily, argon is the most abundant noble gas we have on Earth. So it's 1.3% by weight in the atmosphere. So it's actually very cheap. So you can build a really big detector with argon. So this one shows the 3D image of the events. So for example, this one shows what it looks like for electron shower. So when you have an electron, it's very light. So most of the time, it will just branch along to generate an energy photon. And this photon with pair production produce another electron and a positron. And they would further branch along. So you really will have a very shower-like behavior for this electron. And this plot shows a hadronic shower. You have an energetic proton, and then you hit it with argon, and you produce many mesons and protons. And you can see, you can really take a three-dimensional image of it. And to prove it, let me show you. So this is a three-dimensional view of reconstructed events in the liquid argon. So this is an electron-neutrino charge current event. So you have neutrinos coming in, convert into an electron, and generate an electron shower. At the same time, it's actually hit a neutron out. And the neutron is a charge-neutral particle, so it can travel in the bulk of the liquid argon without being noticed until it hit another argon and generate a few more charged particles. So there's a neutron coming out here and travel to here and interact. And then this actually is a pion. You generate another pion which further interact with argon. So this is a website. You can go there and you can rotate. You can zoom in, and you can look at each of the track carefully. So it's actually a great way to learn about the particle physics interactions. So, and this one shows more pictures. So this one is a neutral pion. So when you have a neutral pion, most of the time they would decay to 2 energetic photons. And then each of the photons would form a shower by itself. So you can see there's 2 of them. So to identify the neutral pion. And with a millimeter scale position resolution, so you can identify a neutrino interaction also out of a very busy environment. So for example, this is you have many cosmic rays, cosmic muons, go through a detector, and then you can see this nice neutrino event sitting there, this V shape. So basically, one of them is a muon, and the other is a proton coming from the neutrino interaction. So here is the summary. So how we're going to have a technology which can help us to differentiate all the different channels and to really separate the signal from background. So liquid argon time projection chamber is a very promising technology. At the same time, it's also a very complicated detector technology, because what we want is a detector goes tens of kilotons, and so we need to be careful and to gradually scale up and practice this new technology. And this leads to the next experiment I'm going to talk about, the microboom experiment at the Fermilab. So this is an experiment with a 80-ton, with a kind of a small liquid argon time projection chamber. So one of the main goals is to practice this technology. And it also has its own physics goal. It's located in the booster neutrino beam line. So using the 8 GeV, so this is the booster. And then you basically have the beam here. And then you have the microboom detector located there. So its primary physics goal is to search the stereo neutrino, search a stereo neutrino, and also measure the neutrino argon cross section. So it is 80-ton, liquid argon in the main volume, and in total you have 170 tons of purified argon. So it's largely designed by the physicists here at Brookhaven. It's 10 meter in the length, 2.3 meter in the height, and 2.5 meter along the drift direction. So it has many innovative technology implemented. The wire readout, the cold electronics, and the optical system. You have a PMT, try to look at the scintillation light coming from the liquid argon, and you have a laser-based calibration system. So this one shows the cryostats, which is used to hold the liquid argon inside of it. And this shows that the optical photons, those photomultiplier tubes installed inside the liquid argon to observe the scintillation light. And this is a picture of the field cage, which is used to generate this very uniform electric field. And this you can see is the cathode plane, and this side will be the anode plane. So this is the anode plane after you installed all the wires. So you have 3 wire planes with a different orientation. And to use them to basically identify so where you got hit in this wire plane. So this is when we push the TPC, the time projection chamber, inside the cryostats and then close the end cap. So the entire detector was assembled in the detector assembly building, and then you need to move into the beamline where you can see the neutrino beam. So it's a field already with liquid argon, and the data will be coming in the next couple months. So now, after all this preparation work, I'm going to finally touch on this mega science project we have been working on to really search for the new CP violation in the neutrino sector. So this experiment is called the Deep Underground Neutrino Experiment. So it again consists of very energetic proton beam. It's a 1 megawatts proton beam to shoot from Fermilab and let it travel to 1,300 kilometers to reach the Stanford Underground Research Facility in the South Dakota. And there will be a 40 kiloton fiducial volume time projection chamber located deep underground. And then there will be a near detector installed in the Fermilab to categorize the neutrino beam. So the entire project worth probably about $2 billion. So it will be achieved in different phases. And its primary goal is a CP violation and also precision measurement of neutrino oscillation parameters. So this is a design of a 10 kiloton liquid argon time projection chamber, and we plan to have 4 of them. So this is just to give you a comparison. For example, this is a diabetes. This is compared to a human. And here you can see for the microboon detector. And on this design, so basically this is a person. So we need to have 4 of them. So there are many, many challenges ahead of us. And many of the challenges really require the younger generation of the scientists to help us to solve them. So here I will just list them as some of them as the questions. For example, you have this promising technology, but how are you going to scale the detector to that big? And then how to achieve a very high purity of the argon? And then how are you going to really do this reconstruction properly to maximize the potential of this technology? And how you're going to deal with this systematics in this measurement where you have so many channels and so many signals in the background. And then it's a $2 billion project. How are you going to have enough resources to really start the construction and to build it? And then it's a very long-term project, and how we can maintain a very healthy field during the process when we construct such a big project, and many others. So here's the summary of my talk. So we are very lucky that CETA-13 is now 0. So it gives us the opportunity to search for this CP violation in the neutrino sector. And we also find a very promising technology, the liquid argon time projection chamber. And its development is very healthy. So we have a dedicated experiment to practice this technology and also to use this technology to do science. And then the design of this next generation long baseline accelerator neutrino experiment is very sound. And it has been a very long journey for us to search for this new CP violation and to explain, to answer the question that why we are made of matter. And our patience will be rewarded, and we expect a very exciting decades to come. Thank you.
So, are there questions, or did you understand every word? Go ahead.
Since the neutrino is chargeless, what does CP violation actually mean? Does it have something to do with the spin of the neutrino, or the helicity of the neutrino, rather?
So the CP violation. So in this. So let me go to the oscillation plot. So the CP violation its appearance in this particular case. It means that a difference in the oscillation probability for muon neutrino oscillate to electron neutrino versus the anti-muon to anti-electron. The main reason we have to search in this particular way is that you cannot have a neutrino by itself. So you need to detect it through an interaction. So the CP violation presents itself as a difference in this probability. Right.
But the neutrino is chargeless. So the C part of this implies that you have a parity violation, and in principle, what does the charge violation mean? Is it actually a change in the helicity of the neutrino?
The charge, I think, it would change basically the neutrino to anti-neutrino. So you have muon neutrino would go to the anti-muon neutrino after the charge operation. Yeah.
Yeah.
So you showed this reactor output, how many particles per gigawatt or something like this. I'm always confused to see the value that's quoted there between gigawatts and megawatts. The electrical output of the thing that normally people are thinking of, or is this actually the energy produced in the reactor because there's a certain efficiency for the electricity production there?
Yeah, it's a thermal power. So yeah.
If I can ask a second question.
Sure.
I mean, when you showed the detectors there, there was this outer layer with this mineral oil kind of shielding or so. Is this instrumented to get a handle on cosmics traversing from the outside, or is this just passive?
So this one is mostly to use this to shield the radioactive, radioactivities coming from the wall, and also the photomultiplier tube. So if you can imagine, you could have a photon, generated during the radioactive decay, which if it hit the liquid scintillator, it would generate a signal, and you could be confused or bury, for example, the neutrino interaction. So this layer is a buffer layer. It's like to reduce the background.
I think maybe, Martin, the point is they're not optically separated. All three layers are viewed by the same phototubes. The vessels are transparent.
Right.
No other questions? Everyone understood everything?
Can I just ask a simple question? What is the time scale for the future detector?
Yeah, that's a good question. So I think the current schedule, we're talking about instrumenting the first one by the 2023. So but of course before that we have a so-called short baseline program. Basically, you start with this 80-ton microboon, and then you want to build another like a 600-ton detector to scale it by 1 order. And then you can go to the future, this 10 kiloton detector. So there will be 4 of them. So they will be constructed one by one, and yeah.
Yeah, I think the point is that every student here will be in the right age group to work on this. Well, I hope not. No questions from the students? I'm amazed. Everyone understood all the nuances of neutrinos. Neutrinos are very difficult to deal with. There have been experiments roughly of this kind for about, 70 years now? And it's only now that people are able to really study them in great detail. And they have been perhaps the most surprising things that we have in this field. You know, when you talk about real surprises, you know, nobody expected, well, maybe there were a handful of people who expected what actually happened. And I don't think they have given up all their secrets yet. Yeah.
If the CP violation in the lepton sector is not enough to explain the observed value of eta, does that eliminate all possibilities within the standard model? Is that then a smoking gun for beyond the standard model?
There are other possible mechanisms. Like, for example, there is some program doing trying to do the electro EDMs, dipole moment. For example, the neutron. So trying to search for this. There's this strong CP, parameter, I think. So that could be another possibility. Yeah, that's as far as I know. That's three.
I had a question. So suppose you got a really interesting answer, like the reaction only went one way, but didn't go the other way at all. All right. How would that affect the matter-antimatter asymmetry in the universe? Or, I just gave you an extreme, but how will your answer, whatever it is, affect our knowledge of the matter-antimatter?
That's a
understanding of it.
That's a very good question. So basically, this the CP violation here is like kind of like a hint of the CP violation for the high energy, at high energy process. So early I mentioned this so-called seesaw mechanism. So basically, the neutrino is very light, and because of that, they actually have a very heavy partner. So in this leptogenesis, theory, the explanation is that it's very heavy. The neutrino partners, they have a CP violation, and when they decay, they have a preference. So that's how you can generate the matter antimatter asymmetry. So there is a link between the low energy, the CP phase that we measured versus the CP phase for the high energy or heavy partners, neutrino partners, and this link is mostly established by model. So you could have different models to connect, just two different phases, and to help us to connect.
So you're assuming that there's some supersymmetry involved? That there's some heavy partner of a neutrino that's not, that we don't see? I mean, we know three neutrinos, right?
So
Too heavy.
right. So basically, it's kind of like the right-handed partner. So what we observe is the left-handed. So if you're in the seesaw mechanism, you would have the neutrino is assumed to be a Majorana particle, so where anti-neutrino naively is just neutrino himself. And then in this case, in addition to this left-handed neutrino, there exists this kind of right-handed neutrino partner, and they can be very heavy. So they.
I don't know, very heavy, like a mass of a proton, or like.
They could be much, much heavier. So the way it happens is the following. So naively, you have this neutrino mass matrix. So you have the so-called Dirac term, where you basically couple the neutrino with, for example, left-handed neutrino with this right-handed antineutrino. But if it's a Majorana particle, then you could have some contribution in the diagonal contribution. So basically, the term is left-handed neutrino with left-handed antineutrino. So if you have that matrix and you try to diagonalize it, and what you will find is that the typical neutrino mass, what we observed, is like a Dirac mass square divided by a Majorana mass. So that basically can explain, for example, why the neutrino mass is so small compared to all the other Dirac particles. Like we have many orders of smaller than, say, the electron. At the same time, then you have another, the other eigenstate, mass eigenstates, and that's actually extremely heavy. So that's the origin.
Okay. Any further questions? If not, let's. Oh yes, one back there.
Just wanted
That's a very good question. I think there are some people proposing to use a cosmic neutrino to check the results. Using the cosmic, atmospheric neutrino is actually very difficult. The reason for that is, you basically can generate, pion, positive charged pion, negative charged pion. So what you're going to have is, very mixed neutrino species. You have a lot of muon neutrino, anti-muon neutrino, electron neutrino, anti-electron neutrino. It's not like in the beam case, you have the beam where you can produce such a thing which is dominant by the muon neutrino, because this is a log plot. So it's like dominant by the muon neutrino. So in the atmospheric neutrino case, you have like all of them mixed together. And then each of them can oscillate to others. You have kind of muon oscillate to electron, and you can also have electron oscillate to muons. So it's extremely complicated environment. But there are some proposals to build a huge detector, like a megaton scale detector, to trying to search for CP violation. So the signal there will be small. And not only it's an even busier environment, but there is a hope to do such a search. But it need to be. I think the first answer, you need to have a very well controlled environment to really convince you'll see this, and then you may want to have another experiment try to further confirm it using a different technique. So it's possible, but it's difficult.